Hello, and welcome to Practical Quantum Computing Part 3, the third of our IEEE Quantum Week tutorial, Practical Quantum Computing from D-Wave Systems. I'm Joel Gottlieb, and over the next hour, we'll be talking about some additional topics. And if you haven't watched them, please track down Part 1, which focuses on binary quadratic models and a history of D-Wave, and also Part 2, which focuses on how to build QUBOs and binary quadratic models, and also talks about running bigger problems by embedding. And in this one, we're going to talk about the following topics. We're going to discuss first the hybrid solver service, allowing you to get classical and quantum performance in one easy-to-use interface. We'll talk about Advantage, the recently released new D-Wave solver. And then I'm going to give you a teaser into the Discrete Quadratic Model solver, another solver recently issued by and released by D-Wave. So let's get started on the hybrid solver service. And the LEAP hybrid solver service basically lets you submit complex problems and get good answers without having to know much about the QPU. And you had in the earlier units, you learned about how to submit problems to the QPU and also how to embed problems onto the QPU. But the advantage to the hybrid solver service is it lets you run problems, even really large problems up to 20,000 variables fully connected. And it takes care of calling the QPU for you behind the scenes. So there's basically the problems run on classical and quantum resources, and behind the scenes the QPU is used, and the interface for it is very easy, which I'm going to show you. And so there's a very short learning curve for this. There's only one parameter which we're going to talk about. So first, let's talk about this hybrid quantum classical approach. It's a portfolio approach in the sense that the hybrid solvers target different categories of inputs and use cases, and each heuristic solver formulates some number of quantum queries which are sent to the QPU. And the classical and quantum components are asynchronous, so that you don't have blocking in the system when the QPU is called. In other words, it can call the QPU in the background and get the results back without interrupting the classical processing that it's doing. At the end of the time limit, which we'll talk about, that's the one parameter, all solvers stop and the best solution is returned to the user, and the user didn't have to decide which solution is best for any input. That's taken care of under the hood. And we've shown some statistics that show that the hybrid approach does win over the classical heuristic-only approach. These two graphs, the left graph for dense problems and the right graph for sparse problems, show definitely a reduced solution cost, measuring the solution quality. Basically, the quantum queries are shown here and also in more recent work that we've just very recently released in the last 2 weeks. The quantum queries definitely show gains in solution quality using this hybrid. And I mentioned earlier, there's only one time limit parameter, which is the time limit t in units of seconds. And the way this works is that the system calculates a minimum time limit that you can put in, which scales with input problem size. And if you don't put in a time limit, it'll just use the minimum that it's calculated by default. And the minimum ensures that each hybrid solver used in the portfolio has enough time to do both a first step and also to query and get a response from the QPU. And right now the minimum time limit is 3 seconds and the maximum time is 24 hours. And we suggest running the problem first without a time limit, for example, to get a feel for it. The program actually will tell you what the minimum time limit calculated is. If you run it and your input time limit is too small, it'll tell you what the minimum is so that you have some idea. And as I mentioned, it's really easy to use. Just these 3 lines, basically. The first line being the import of Leap Hybrid Sampler, and then the second line instantiating the sampler, and in the third, you're actually calling it sampler.sample, like we did with our other solvers. And the time limit there is shown, in this case as 5 seconds, although as I mentioned, it's a default to use the minimum that it's calculated. There's no embedding to worry about, and there's no chain strength to think about here. So this is really a very easy to use solver. And let's look at the code changes that you might make if you want to use this on a much larger problem than the QPU can solve. So basically the blurb I've shown here, import the Leap Hybrid Sampler, and then instead of the binary quadratic model class that we used in the previous unit, we use one called adjustable vector BQM, which is designed to handle much larger BQM problems. In the third line there, we're setting the offset in this particular problem, which, as we talked about in the previous unit, is a constant, which might be able to use, you might want to use to define the energies relative to a known 0. And then in the next lines, we're adding variables and interactions to the BQM. And finally there in the 6th and 7th lines, call the sampler and after instantiating it. And so this is really all you have to do to use the hybrid solver service, designed to be very simple to use. And so now let's work a well-known problem, another one of the problems that's in Andrew Lucas's list of QUBO problems, which is the famous knapsack problem. Let's run that. Let's set it up and run it with the Leap hybrid sampler, the hybrid solver service. And so here's the knapsack problem if you're not familiar with it. You want to pack a shipping container or a knapsack or a backpack or something like that. And you have a collection of objects. Each object has a weight W sub I and a value V sub I. And the goal is fill up the container so that we obey a maximum weight W. In other words, can't overload it. Can't put more weight in there than we're allowed to. In the case of the backpack, I don't want to ruin my back, or shipping container might have rules before it's put on a ship about how much it can weigh. And just to give you some real-world examples of knapsack problems, choosing which ads to bid on in internet ad auctions on a fixed budget. In other words, you've only got so much money to spend, and certain ads are more valuable than others depending on how much your clients are paying. So which one should you show? The Forestry Service has a certain number of land packages it wants to buy with fixed budget. And actually the limit is the budget, but you also want to maximize the best land you can buy, or even just financial portfolios. You have a fixed budget. How many and how much value can I get out of this portfolio? So now let's get started on building the QUBO for knapsack so that we can run it. The objective is maximize the total value of the selected objects. And the constraints are the total weight must be less than or equal to this number W, which is provided. Step 2 in building the QUBO is to set up reasonable binary variables. And so in this case, we're just going to ask, is this object in the knapsack or not? And so we can just use the binary variables to label the objects. X sub I, X sub 1 for the first object, for example, is 1 if object I is in the knapsack, and it's 0 if the object is not in the knapsack. And so now, given these variables, let's take a stab at writing the objective first. And a first guess would be minus the sum using alpha for the index of V alpha times X alpha. And what that does is that's going to minimize the sum of values, make it as negative as possible, give us the most value, if you will. And the reason it works is that if X is 1, of course, it's in the knapsack and it'll count against my total. Remember, the V's are the values of the individual objects. So this is a first step in the QUBO. And then let's try to write the constraint. And based on the knowledge that you picked up in the first and second parts of this tutorial, you would know that a good guess is to take W, the total, minus the sum over alpha, W alpha X alpha, because that's just going to sum up all the weights, and square it, right? Because we remember that we could have a parabola. We'll find a minimum where they're going to be equal to W. And we put a Lagrange parameter, just call it A, in front of it. In this case, it was gamma in the last unit. But there's a problem here. This isn't quite good enough. This is assuming that W is supposed to be equal to the sum of the weights. But we want it actually to be less than or equal to. Remember that from a few moments ago. So what we have to do is we have to add what are called auxiliary variables so that it might be less than by 1 or less than by 2, but we're allowed, in other words, if I've got a 40 kilogram pack, well, that's a big backpack, but in any case, I could have 39 or 38 filled up to that point, and that would be good enough. So the less than or equal to is important in this solution. And here's the QUBO that we come up with, and this is due to Andrew Lucas. The first reference down there at the bottom is that original paper that you know about, and then he modified it the following summer, that summer in Zurich. But we basically have the Hamiltonian in equation 4 there, where what we've done is instead of W, you have a sum over these numbers C sub I, which are powers of 2, times some auxiliary variables Y sub I. And those yi's, you want to think of them as they could be 1, they're going to be set, they could be 1 or 0, of course, they're binary, but they could be set to provide sort of the fudge factor between, say, 49 pounds and 50 pounds, things like that. We wanted the overall condition to be less than or equal to, so we're using those variables to kind of allow for the possibility of less than or equal to. So this is the formulation that we're going to implement. And so I wrote a Python program in Ocean to do this, and basically the first few lines just set up the cost and weight dictionaries in Python, and then we have this code available actually in the D-Wave collection of examples. Just look for knapsack and you can download this code. But for our purposes here, the bottom lines are what's important. We're going to use the Leap hybrid sampler, that is the hybrid solver service. We're going to use it to run this code. So here's some results that we got when we ran the HSS on a small data set. Not very many objects here, but you can see, just to get familiar with this sort of data, on the left side is the value of each object and the right side is the weight. And HSS finds the solution very quickly using the default time limit. In this case, it chose to take the objects weighing 20, 10, and 15. That is the last 3 rows. And the energy has been, using an offset, has been set so that the minus of that of the sum total of the values will give the energy. So that's another way to check that this problem is working. But Hybrid Solver Service did very well on finding the solution of this small problem. But then, of course, the real benefit comes when you run on a bigger data set, which can't be embedded on the DW2000Q. 68 objects, and the Hybrid Solver Service finds a solution quickly. Again, the solution is there in the middle. The weights do satisfy the constraints. They come up to less than 70, and the energy equals the summed objective. They add up to 524. So in this case, the Hybrid Solver Service has done very well. And as I mentioned earlier, this example is in the github.com D-Wave examples repository. Please download it and play with it. And there's a couple more even bigger data sets in there now that you could explore with the Advantage solver. So let's conclude this part of this tutorial by summing up what we've learned, that this particular problem is too big for the QPU. The Hybrid Solver Service makes use of the QPU in the background for us. And one interesting research question is, if you run this yourself, and please do, please download it and run it, you'll see that it doesn't find the minus 524 solution every time. And so it's a research question. Will it find it every time if I give it a lot longer run times? Just sort of an interesting question to me. But let's now move on to our next topic. And we're going to explore the Advantage chip. As you saw the announcement a couple weeks ago of Advantage, let's have a look at it and talk about some of the very exciting details. And so if you were with us on September 29th, you're aware of our launch of the Advantage machine, the most connected and powerful quantum computer built specifically for business. And I'm going to talk a little bit more about what we mean by that coming up. And the first thing is that we do have a new processor architecture. We're going to talk about the layout coming up. We want to be able to handle much larger and more complicated problems. We did get past 5,000 qubits, more than that, and we've also increased the connectivity between qubits. You remember that in the Chimera architecture, each qubit had 6 neighbors, and we're going to see shortly that the number is considerably bigger than that. So here are a few more of the details. The annealing design has more than 35,000 couplers, actually, again, which is a 5 or 6 or maybe a little more times factor from Chimera. In the fabrication, there's over 1 million Josephson junctions, and that in itself is an interesting thing to consider, that the whole idea of a Josephson junction only goes back 45 years. It's kind of interesting that we've got something that has so many. And as I mentioned, the new topology will offer much better embeddings, which I'm going to show you coming up. And you'll be able to embed much more complicated problems. And here's a few more details of how we brought this together. As you know, and we talked in the last presentation, the longer chains don't perform as well. And so Advantage has up to 50% shorter chains. We'll see that coming up. And we've just started doing some of the research to show this. But in one fully connected example, the Advantage system returned optimal solutions that were 42% larger than inputs solved by the 2000Q. So definitely doing much bigger problems. And we've also increased the size of the Hybrid Solver Service that we talked about earlier in this unit up to 1 million variables. And basically the whole infrastructure's been updated to support Advantage and an improved hybrid solver. So we're pretty psyched about this. And so this slide just shows how we've integrated Advantage in with Leap, of course. So users on September 29 were already submitting problems to Advantage within an hour of the launch. It basically didn't have to change too much, and I'm going to cover all you have to do coming up in Leap. You basically hardly have to change anything in order to utilize the Advantage machine and the updated hybrid solver. And what I meant when I said that we're built for business is that we want to write, we want to encourage people to write, that is, production size applications that use the quantum computer. Not just toy problems, not small ones, because we've been doing that for a long time, and it's part of quantum showing its future superiority. But we want to contribute to this immediately by showing companies that they can put a production scale application on Advantage. And I want to mention just one more thing here, that nice little graphic here that I wanted to show you of the Advantage processor, but also that the embedding of three-dimensional problems has gotten a lot better. We were able to embed an 8x8x8 problem. You might have been familiar with the material science work that was submitted by Andrew King and others, and Richard Harris and others a couple years ago. Please look on our website if you're interested in the references. But Advantage is going to embed a 15x15x12 lattice, and that's basically going to allow a lot more condensed matter research to happen on this machine. So we're looking forward to that kind of research, in addition to people doing the business work that I talked about, putting those production applications on. So all in all, you can tell that we're really excited about using this machine and about getting the world to use it, getting people to put their production applications on and seeing how they perform. So what I want to do now is dive in a little bit to some of those details for you. Remember with the Chimera graph that, of course, as it says here, the underlying architecture looks like a graph. In this case, these nodes are, the dots are qubits, and the edges are couplers, and the unit cell is shown there in the inset. 0 and 3 across the horizontal row, it's, if you can see the numbers there, are horizontal, and they don't connect to each other. And then you have this vertical column, 4, 5, 6, 7, where they do not connect to each other, but they connect to ones in the row. And each qubit also has two external couplers that are not shown in the unit cell. But example, if you look across the top row of the lattice there, you can see that each qubit has one on its left and on its right, in addition within the cell. And if you look, say, across the right-hand column of the figure, you can also see that each qubit there has a neighbor above and below. So basically each qubit in the interior has 6 neighbors. It has neighbors either left and right or above and below in the lattice, as well as inside its cell. It has 4 other neighbors, so 4 plus 2 makes a total of 6. And the family of topologies in this case is called Pegasus, which is written P of n or P sub n, with a total number of qubits equal to 24 times n minus 1. And so now one interesting thing that we're not showing is that the qubits layout actually has some that are disconnected and not in use mathematically, so we'll ignore those. So for the P16, if you put in 16 for the n there, it'll come out 5760, but 130 are disconnected. So there are 5,640 usable qubits in the P16 Pegasus graph. And one thing that's interesting is you can see that the Chimera architecture sort of has a footprint in here. You can see in the unit cells, or what look like unit cells there, that the basic little eights are there from Chimera, but they're different here, which we're going to talk about a little bit more. Here's a reference document, by the way, if you want to get all the details of the Pegasus graph. And I'm going to hone in here on a P4, which just it'll just give us a feel for it. The Advantage machine is a P16, but in a P4 we can show the entire thing so that you can get a look at it. There are 288 qubits in a P4 layout, and I should mention that the Ocean Toolkit has lots of functionality designed for being able to visualize the Pegasus graph architecture. So you can look in the documentation for that. But one, as I mentioned just a moment ago, one can see groups which look like Chimera, but here's one key to it that's different. Hone in on that little Chimera-looking thing in the lower left. And there are basically now additional couplers inside the rows between what used to be 0, 1, 2, 3, and inside the column between what used to be 4, 5, 6, and 7. And there are also what are called odd couplers, which are parallel qubit pairs in adjacent rows or columns. So if you look across the top, you'll see that there are two by themselves. See that? And they're connected to two more across the top, and likewise across the right and the bottom and the left. And part of what those are there for is to connect those long rows that wasn't possible in the Chimera. And a lot of this redesigning, these in-row couplers and in-column have a tremendous benefit in terms of increasing the connectivity of the lattice. And that's one of the reasons they're there, is just really to make it overall way more connected than it previously was. And so to give you a feel for some of the benefits, I'm going to have to introduce a term from graph theory, which I myself had to learn to do this since I'm a physicist, not a mathematician. But for a clique, that is for a structure where every node has an edge to every other node, or a complete graph, if you like, we call them K and then with the underscore. So K4, for example, would be a 4-node clique shown on the left, and K8 is an 8-node clique. So again, that's a complete graph. Every node has a connection to every other node. And embedding a K4 on Chimera and Pegasus is one way to show the benefit of Pegasus right away. You can see in the Chimera in the middle of the picture here that embedding the 4 clique on Chimera meant 4 chains, each of length 2. In other words, requiring a full unit cell, requiring 8 nodes to do it. And on the right, you can see that Pegasus embeds this trivially, 1 node to each physical, 1 logical variable, 1 logical qubit to 1 physical qubit. And this is really nice. In other words, you could say that the K4 is native on Chimera and Pegasus, and that was, again, one of its design principles, was that you could do this. And I'd like to introduce another piece of graph theory terminology here, which is Kn, n, what is called a biclique, where each node on one side has an edge to every node on the other side, but not on its own side. And so K4, comma 4 on the left there, it's a little hard to see it because my drawing in Python isn't great. But 1, 2, 3, and 4 form one side, and A, B, C, and D form the other side. And so 1 has links to A, B, C, and D, and 2 has links to A, B, C, and D, but 1 does not have any links to 2, 3, and 4. So if you like, you could picture 1, 2, 3, 4 on one side and A, B, C, D on the other. And then it's not that much easier to see on the right, but 0, 1, 2, 3, 4, 5, in this case it's a K6, 6, are on one side, and A, B, C, D, E, F are on the other side. And you can sort of see that across the top there, 0, 2, and 4 do not have links to each other. They're just basically connected to all the edges, all the nodes on the other side. So that's a bi-clique, like K6, 6. And so if we embed this, again, on Chimera and Pegasus, if I look at the middle picture, that's Chimera, and you can see that for the most part it's chains of length 2. And in fact, I'm not seeing any more than 2 on any of these. If you do, let me know. But like the dark blue and the red and the dark green and the pink and so on, those are all chains of length 2 on Chimera. But if you look at Pegasus, those are all unique. In other words, in this case, it's one physical node to one logical qubit. And so basically the K66 biclique is native on Pegasus. In other words, it just embeds and without chains. And this is going to have, I believe, really decent performance improvements that hopefully we'll see as people begin to do more and more of these problems on Pegasus now that it's out there in the world and running problems. Going to be very exciting to see how well this works and see the performance. And just summing up a little bit of what we've learned here. Pegasus embeddings use fewer qubits and shorter chains. And K4 and K66, now you know what those mean, are native. One logical variable, one physical qubit. And again, here's a link to the reference document where you can find out more about this. But I'm hoping to motivate you to embed and then solve some of your complicated problems on the Advantage solver. Now, here's the very simple thing you have to do in order to change from Chimera to Pegasus. And as I said, even within a few minutes, under an hour of the announcement on September 29, we were getting reports that people were already running problems on Pegasus. In the line here, first you have your import of D-Wave sampler, but then in the middle line there, you can specify Chimera as the typology type. And here you can do the same thing for Pegasus. You just change it to Pegasus, and that'll focus on the currently available Advantage machine. And that's it. That will start running your problem on the Advantage chip. And this has been possible with Chimera as well, but for your reference, I want to show you that you can get the properties of the particular chip. In this case, what we've done is we've set up the sampler as Pegasus, and then in the third line, we've asked for the properties of the Pegasus sampler, and then we're just printing some of them out in the lines after that. So the couplers, the H and J range, the number of qubits, etc. And just briefly, you can see that if you print the number of couplers, and please do this, you'll see that it's on the order of 6 times more than Chimera, indicating that vastly increased connectivity that I talked about. And here's some code that shows little bit of what you can play with and what you can do. In this case, to draw and embed a clique. The first line, minor minor, in use here, the bus clique new software to do the clique embedding algorithm that I talked about in the previous presentation, and for cliques and an improvement to the Chi-McCready and Roy algorithm. We're calling for the Pegasus solver, and then we're going to get a list of the couplers on the actual advantage solver, and then we're going to get a Pegasus graph, in this case a 16, a P16, using the edge list, and we're going to find a clique embedding based on that actual Pegasus graph. And then this last thing makes it really easy just to draw the Pegasus embedding. So I encourage you to play with this, even though you could see one of my own shortcomings in drawing one of the figures. It's fun, but it's also very interesting to see how well this advantage chip really does. And so that wraps up our explorations of the advantage chip and architecture. Please use it. Please get started on LEAP if you haven't, but please make heavy use of advantage. And now what I'd like to turn to is our third topic, another one of our hybrid solvers, the Discrete Quadratic Model solver, or DQM solver. And what I want to do now first is motivate it. What does this mean, Discrete Quadratic Model solver? And I'm going to start by reminding you of what a QUBO was from the first presentation in this series. QUBO meant that the highest power of variable appearing was 2, no constraint, no forced constraint, that is, applied to the variables. In other words, we're going to solve the problem and let it find whether the constraints can be held. The variables take their values from 0 and 1 only. It's binary. And we're going to minimize or maximize an objective function. And you'll remember that we also referred to these, when we got Ising in the picture, we referred to them as binary quadratic model. And to change this to a discrete quadratic model, all I need to do is change that third line. The highest power of variable appearing is still 2. No constraint, again, that is, no force constraint is applied to the variables. The variables take their values from 0, 1, 2, and 3, and we're going to maximize or minimize an objective function again. But so you can see that the third line is the key here. The variables are allowed to be non-binary, that is, some set, 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, etc. There's some set of values that they're allowed to take instead of just being binary. So here's just a few initial thoughts of problems for the DQM solver. And an initial one is team choosing, team picking, with more than 2 teams, where a player, for example, in the NFL draft or something, could end up on only one of many teams. And then consider something like graph coloring, where we want to assign a color to each particular node, and we don't want neighboring nodes to have the same color, but there may be more than one color option. So that's a natural thing for this solver. Graph partitioning, for example, if we want to divide a graph up into a specific number like we solved in the second unit in this series, the graph partitioning problem, we wanted to have partitions where we had as few links as possible in between partitions. And I've added the fourth line here as an encouragement to you in that your business problems may very well fit naturally to this. Something where you have more than 2 options and it's not really binary. Won't have to do the programming to turn it into binary here. The idea is to try to run it through this solver where we allow it to have a set of values that it could take. So let's now explore one of those problems in more detail. And so here's a well-known problem, another one of Andrew Lucas's basic 21 NP-hard problems, which is graph coloring. Assign colors so that the neighboring nodes have different colors. Simple enough. And so here we're dealing with 7 nodes. Septagon, I might call it. I'm not sure that's really correct. But in any case, hopefully you get the idea. We want to put colors on these nodes so that all neighboring pairs have different colors. And so what does a solution look like? So let's look at a solution to this problem here. If we start at node 0, notice it's green, and node 1 is red. So that shows that they're different. 1 and 2 are different, 2 and 3 are different, and if you go all the way around, yes, they're indeed different. And how many total colors did we need? In this case, we just needed 3. Green and red and blue. So this is indeed a solution to this graph coloring problem. And so what we want to do is solve this with the DQM solver. And so the first thing is, how do we program the DQM solver? And so the first question is defining the variables that the DQM solver is going to have. And the way this is done is to define the variables on a set. In other words, DQM variables can take one of a set of values. So for example, in this case, if we want to write a program for graph partitioning, node 0 can have one of 4 colors: red, blue, green, or violet. You can think of this as an enum or defined over a set, however you like to. But the main point is that we're not in binary variables any longer. This is defined over a set, and it's a DQM variable. Now, another important point, that's the next point on the slide here, is that the DQM solver automatically implements a one-hot constraint on its variables. We're not going to have to program the one-hot constraint. The DQM solver, when we define the variable this way, it's going to know that we want this to be one-hot, that only one of the colors is going to be turned on in the problem. And so this is going to be hugely useful when we go on to solve more complicated problems. And so to sum up, what do we need to tell the DQM solver when we define a variable? We need to tell it the name of the variable, and we need to tell it the values that the variable can take. And this information is going to be loaded into a DQM object that will then pass into the DQM solver in a little while. But first, let's turn to the next thing, which is how do we define a variable and how do we load it into a DQM object? And so here are the things that we need to do to define a DQM variable, all in this block of code here. The first couple of lines first import the Discrete Quadratic Model class, and then we define our colors, that there's going to be 4, and the range will be of use later. But the next thing that we do is instantiate a discrete quadratic model, which is going to receive the variables that we want to define. And in the next couple of lines, we set up a network X graph just representing this hexagon that we looked at pictures of just a few moments ago. You can see 0 to 1, 1 to 2, and so on until you get back to 0 to 6, closing the, excuse me, not the hexagon, but the septagon, the 7-sided figure, closing the loop. And then finally, in the last two lines, we're going to loop through all the nodes. So 0, 1, 2, 3, 4, 5, 6. And we're going to add variables for each one. And each one is labeled by its number. So one called 0, one called 2, one called 4, etc. That's the second argument there is the DQM variable name. And then in the first argument tells it that there's going to be 4 values for this, 0, 1, 2, 3. And we just say add variable, and that'll take care of it. So this is the way that we put the DQM variables into the DQM object. And what we want to do next here then is tell it how the DQM object's variables have to interact. In other words, we're going to want to put biases on them so that we can get the result that we want. Now, in the DQM model, we have two kinds of biases. We have linear biases and we have quadratic biases. And so let's do the linear biases first. What we need to do is tell the DQM solver how we want to use these colors. In other words, earlier you saw that the variables are really node and color pairs. In other words, node 0, and then it can take on one of the 4 colors. And one way to bias is to favor using as few colors as possible. And one way to do that is just to say, okay, if you use red on a particular node, you'll have an energy cost, a bias of 0. If you use blue, you'll have a cost of 1, and green 2, and violet 3. And this is arbitrary. You could set other values for this biasing. But this is going to favor the low-numbered colors, and we're going to use the quadratic biases to insist that the neighboring nodes do not have the same color. That's going to come up next. But the first thing to do is just set the linear biases here so that we are going to favor as few colors as possible. And you can see at the bottom here, just the 2 lines that I've added. We're just simply going to loop over those nodes again. So those are the, basically there's one variable for each node, as we talked a couple of slides ago. And each of them is labeled just by its node name, 0, 1, 2, 3, whatever. And notice what this line is saying. Set the linear variable to, and colors is in that 3rd line above. Remember I said I'd get back to that. That's a range from 0, 1, 2, blah, 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 up to the number of colors. And so what this is basically going to do is set that variable so that, as we saw in the previous table, color 0 will go with a bias of 0, color 1 with a bias of 1, color 2 with a bias of 2, and color 3 with a bias of 3. And I will refer back to this when we get done, so you can see how it worked. But the next thing we need to do now is set the quadratic biases, and then we'll be done and we'll be ready to run the program. So here's the table of quadratic biases that we're going to set. You can see that we basically have to consider all pairs of nodes that are edges. So the first edge in the graph, if you like, is from 0 to 1, and I've shown that here. I've shown some of the combinations. If you think about it, remember that each node can have 4 colors, so there's 16 combinations. And so I'm showing a few of them here. Color on the left and then color on the right for node 1, and 0, 0, 0, 1, 0, 2. And what you can see in this table is that I've put a bias of gamma, that is the Lagrange parameter, on any of the pairs where the colors are the same. So it'll be 0, 1, and 1, 1 there at the bottom, and I didn't show all 16. But you also know that there's many edges in the graph. So there's going to be 16 times the number of edges in terms of labels, in terms of rows in this particular table to set the quadratic biases. But we can see that what this does is it's going to penalize the system. The DQM solver is going to penalize the pairs, the edges that have the same color. And so what we're trying to do here, basically, if we join it in with the constraint that we put on the linear biases, we're trying to get it to use as few colors as possible, but also do not have neighboring nodes have the same color. So hopefully you get the idea. And what is this going to look like? But first, before we do that, let's look at how we would program this. And here's how it looks in a program. I've removed a few of those earlier lines because you already know them. But you can see on the bottom for P0 and P1, those are going to be the edges. So we'll be referring to, say, node 0 as P0, node 1 as P1. And what we're doing there on the right is called a dictionary comprehension. It's going to create a little dictionary that will have values of Lagrange whenever the colors are the same for seeing color, so 0, 0, 1, 1, etc. And they'll automatically have values of 0 for any other combinations. And so in this way, this single line here takes care of all these combinations. And so now we've got the quadratic biases ready. And let's put it all together in a program. And here's the program all put together. We're going to, I've included just those last couple lines from the previous sections, setting the quadratic biases. Then we're going to call and instantiate the Leap Hybrid DQM sampler. This is the DQM solver. We're going to solve the problem, just sending it with sample DQM method, and just send that DQM object that we constructed. And then we're just going to get the sample and the energy, that is the first lowest energy solution, and just do a simple check to see whether indeed the neighboring nodes do have the same colors or not. In other words, I just called it validity there just because it's either going to be true or false depending on whether the neighboring nodes have the same color. If any neighboring nodes have the same color, it's marked to false. And so let's now go ahead and run this and see what we get. Okay, and when we ran this on the DQM solver, here's what we get. Node 0 takes color 0, node 1 takes color 1, node 2 takes color 0, 3, 1, 4, 0, 5, 1, and you think you're going to be able to do that, but you're not. Node 6 has to take color 2. Notice that node 6 can't be 0 because if it were, it would have the same color as node 0. So we needed the additional color 2. And so that's why I wrote there we need green, that's color 2, on one node. And the question for you just to ponder quickly here is, why is the energy 5? Does that sound correct? And if you think about it for a minute, remember that when we set the linear biases, we chose to penalize the use of each color by its a bias equivalent to its color number. That was arbitrary, but that's what we did. So the use of 0 doesn't cost us anything. The use of 1 costs us 1, and the use of 2 costs us 2. And so you'll see in there for the 7 nodes, we used 1 3 times, and we used 2 1 time, and so the total is 5. And the energy checks out, and woohoo, we've got a valid solution. I'm hoping that you've enjoyed this brief, what I would call a taster, sort of a preview of the DQM solver. I'm hoping that I've convinced you to use it and apply it to some of your problems. And let's conclude. And so summing up you saw that HSS, the hybrid solver service, is very easy to use and runs really well on large problems. We saw that for knapsack, so hopefully I've encouraged you to try out the hybrid solver service. Please try out Advantage. Your problems should perform significantly better given the shorter chains and all the other engineering work that went into this. As we like to say, a million Josephson junctions for something that didn't even exist until the mid-70s. Pretty cool. And then also try the Discrete Quadratic Model solver. It's a little different, you can see that, but it also is targeted at very large problems. It is also a hybrid solver with a classical and a quantum part, and we're very much looking forward to seeing the types of problems that users like you are going to come up with. And finally, thank you very much for listening. I'm Joel Gottlieb. I'm with D-Wave. This has been the third of a tutorial series for IEEE and for qubits. And please sign up for LEAP and use all this software and all these machines. Looking forward to hearing from you. jgottlieb@dwavesys.com. Again, thank you very much.